Okay, here is the new homework. Okay, so if you look on the syllabus, we're not actually having class next Tuesday. They put a couple breaks in. Next Tuesday, there's no class at Alfred, just because of the way they did the schedule. What? Tuesday, next Tuesday. You can put them right up there, Dirk. And then, you know, with the test being on Friday too, so if you look at the date on this, it is March 2nd. So when you look at March 2nd and wonder why that's the reason for the late date. You can pass some of these back. Thanks. Yep. There you go. And you're by yourself in a whole aisle by itself. Okay. There you go. And as promised, solutions to life, society, all the solutions you could possibly need. You're welcome. Okay, does everyone have the new homework and the solutions? You sure? How many? Just one? Did you have solutions? There you go. Okay. So does everyone have the solutions and then the new homework? Okay. Has everyone handed in their homework? Who's going to be handing it in? Okay. You guys good with this? Do you need more? We're good? Okay. So when is our exam? Thursday, and that is going to be 6 o'clock, and it's part one of the exam. There's some, I know with the Zoomers here, what I would like you to do, unless you are quarantined, I would like you to actually be, or have some official reason, I would like you to actually show up to here to take the exam. It's just going to be a whole lot easier. Yes. Not right now. We'll do it later. Okay. So unless you're actually officially quarantined, I would like you here actually taking the exam, and that goes for Friday as well. What? Then I will send it to you like that. So if you're quarantined, I will then send you the exam, but send an email to me stating that you are quarantined so I can actually officially check this out. And then I will actually send you then the exam so you can then take it. And the reason why I'm doing that, and I'll be quite honest about it, is that in the spring when everything was online, the amount of cheating from online was absolutely phenomenal. And so that's why I don't want to do anything online, because it was a complete disaster when we did it in the spring. I'll be generous and say only 70% of the people cheated. I'm being kind and I'm being generous. I think that the incidence of cheating was actually significantly higher than 70%. And so I don't want to deal with that again. Okay, with that said, one thing I'm going to be doing slightly different from what I told you about. I told you before in part 2, I was going to have that dot product part question. I'm going to move that to part 1. So I'm going to kind of tinker with it, make it a little bit shorter. So you're going to see that type of problem in part 1. Okay? Questions? Okay, with that said, we'll start. So we're going to go all the way here. Good. Okay, so we're looking at special relativity. And we said you're going to ask something really bizarre in special relativity. What's the really odd thing we ask in special relativity? Seems kind of dumb. We're going to relate two measurements. We're going to have a stationary frame. So this is stationary. What do we call the stationary frame? Just S. So S is going to be the stationary frame. And then you're going to have a moving frame. And with the moving frame, it's going to be just like the stationary frame, but you put primes on everything. So this would be x prime, this would be y prime, this would be s prime. And this is moving with some constant velocity, v. Like that. And we're going to have an event. What did we say an event is? Yeah, is anything happening at any location at any time. So this is an event. So this person here, the stationary observer would say, oh, this occurs at x and y at time t. Whereas what would the moving observer say? This is our moving observer. The moving observer is going to say that same event has these coordinates. They're going to say, oh, it has this coordinate x prime. It has this height here, y prime. And it occurred at some time t prime. Whereas the person over here says, no, that event occurred over here, this distance x. And then this distance here, y. And then this time t. So they're both measuring the same event, but the positions and the times are going to be different, potentially. That's all you do in special relativity. You relate these measurements to these measurements. That make sense? Okay, so what are you going to do with this? We said there's something called the Michelson-Morley experiment. And what did that show? It showed a very odd result that no one was expecting this. Yeah, so what this is going to show is that if you measure the speed of light in a vacuum, it doesn't matter whether you're moving toward the light or away from the light or up, it doesn't matter how you're moving. Everyone will measure the speed of light to be the same. So this states that all observers measure the speed of light in a vacuum to be the same. And what do we call that value? C. Okay, so whenever you see a C, it's going to be the speed of light. Let's get some values for it. I think most people know what it is. C is good. Meters per second. So if I just say go like this with your arms, how big is a meter? Meter is about yay big or so. Okay, so what is this? This is really 300 times 10 to the 6. 10 to the 6 is what? A million. So that means that every second, light travels, if this is the meter, travels 300 million of these in a second. Okay, that's almost impossible to fathom that speed. Okay, but that's what this means when you measure it. If you convert it to miles, I don't know what it is in terms of miles. 186,000 miles per hour, miles per second. So when the space shuttle Columbia broke up in the atmosphere, they stated its speed. It was something like, what, 10,000 miles an hour or something. You think pretty high. You think 10,000 miles an hour, that's really booking. You compare that to the speed of light, it's absolutely nothing. Okay? This shows you how far away the sun is. How long does it take sunlight released from the sun to reach us on Earth? 7 minutes. Yeah, about 8 minutes or so. So the fact that it takes 8 minutes, that tells you just how far away the sun is. That's really amazing. Okay? So it doesn't matter whether you move, if you have laser coming at you, if you're moving toward it, up like this, it doesn't matter how you move, your speed of light is going to be the same. It's going to be c. Again, no one believed that result for a while. Certainly Michelson certainly didn't. That's why he kept on perfecting his device, even though he realized it had been perfected a long time ago. Einstein comes along and takes this serious. So this is the first postulate of relativity. There's only two things we need to get all the results from special relativity. This one here, and then the next one. So let's talk about the postulates of relativity. Postulates of special relativity. Okay, so I used the word there, postulate. What does it mean to be a postulate? Yes, then you have good posture. Okay. What's a postulate? Could you speak louder? Or, okay. Okay, so yes. Yes. Not when you use it mathematically. What's the mathematical idea behind it? Yes. Yeah, they're going to be kind of some sort of initial starting point here. Okay, so they're kind of the initial assumptions you're putting into your theory. So the first assumption you put into this is the Michelson-Morley experiment. The first postulate is that all observers, it's going to be this thing here, all observers measure the speed of light in a vacuum to BC. So that's straight from experiment. Okay. The next one is kind of an odd thing, and you probably have had experience with this. It's just you haven't really thought about it this way. The next statement is the following: if two observers are moving with a constant speed relative to one another, it is impossible to do an experiment to determine which observer is moving. Okay, so let me give you an example of this. So when I was in graduate school, I did my graduate work in Illinois, and my advisor had a number of people up at a national lab. I had to go up to the national lab to work with them. And they're up in Chicago. And so you'd have to take these trains to Chicago. And if you've ever had the unfortune of having to take trains to Chicago, they're always off. Maybe it's just true with trains in general, but these trains are never on time. So I was on a train waiting to go to Chicago, and we were, I don't know how many hours late. We were not moving. So you get comfy in your chair, and I looked out the window, and I could see things moving. I went, finally, we're finally moving. This took forever. So I got up in my chair, and I looked at the ground, and we were stationary. We were not moving. It was actually the train over there that was moving. We were stuck. The train was just so large, I didn't feel the acceleration of it moving it. Plus, I was sleepy. That's what this means here. In other words, if you have a case like this, let's say I have two spaceships like this. And let's say this person is saying this guy is coming at them with some velocity v, that's constant. So this person says, oh, you're coming at me with this velocity v. But what would this person say? That person would say, no, you don't really know what you're talking about. You're actually coming at me with the velocity v. I'm stationary. Now you could say, well, wait, this is stupid. You know what? You've accelerated your spaceship. And that's true. But this only applies once you have a constant velocity. So the postulate states that try to do an experiment to state whether it's this case or this case. You can't. That's what the postulate states. You can't do an experiment to determine whether this is a situation or this is a situation. You may know, because you may have seen one, you might know that you're stationary and you see this guy speed up toward you, then move with a constant velocity. That's different. Try to do an experiment to determine which of these it is, and you can't. That's the second postulate. That's all you need, and then everything else comes out naturally from those two postulates. Okay, so with that said, I want to get the first idea behind here. So any questions on the postulate? Oh, the other thing, you can never use a theory to prove the postulates. So once you get your theory, you might say, I'm going to use my theory, and I'm going to prove those postulates. You can't. The postulates are your initial assumptions that go into the theory. Once you have your theory, you can't prove the postulates from that theory. That's not possible. So the first thing we're going to do is something called time dilation. Okay, and this is one of the big things you get from relativity. It's really kind of an odd thing. So to get this, we're first of all going to have a weird clock. We're going to have something called an Einstein clock. So what on earth is an Einstein clock? This is an Einstein clock. We're going to take a laser here. So here's a laser. We're going to fire the laser beam. There's going to be a mirror here. And I said the distance from the laser here to here, and I call that L0. That laser beam is going to come up here, hit the mirror, and reflect. Okay? I'm going to say the time it takes for the laser to do that to be 1 tick of the clock. So you send out like a laser pulse that comes up, comes back. That's kind of 1 tick of the clock. You send out another pulse that comes, it comes back. That's 2 ticks of the clock. Then 3 ticks, 4 ticks, 5 ticks. That's how we're going to measure time. Okay? So 1 tick. Of the Einstein clock. Is the time it takes light to travel to and from a mirror. Okay? So you tell me, and we're going to call that time, we're going to call this time delta TP. Don't worry about why the P is there. I'll explain the P in a second. So you tell me how to find that. What would then be 1 tick of that clock? What distance does the light travel? L naught? Almost. The light travels to L naught. It goes this way, L naught, and then this way here, L naught. What speed does it travel with? If it's light, c. It has to be c. And there's no acceleration. So if you know the distance, if you know the speed, how do you find the time? Right, you can do your x equals x naught plus v naught t plus 1/2 AT squared. I can take this to be, I'll say my distance is going to be 2L. That's the distance I'm traveling. My V naught is C. My time, I'm calling this delta TP. My acceleration is 0. Okay? So I get this right here. And I'm going to put this over here. So I get this 2L naught equals C delta TP. Error, I can still see that. Over 2. Let's stop there. Does that make sense? Questions to that? Now here's where the relativity comes in. We're going to take this clock, put it in the back of a truck, and drive down the road. So here I am, I'm stationary. Here's a truck, the driver, here's the Einstein clock. That truck is driving down the road with a velocity v. Okay, what did we say 1 tick of the clock is? 1 tick is the time. Yeah, so 1 tick is the time it takes for the light to go from the laser to the mirror and then back. Now let's ask a question. What does the stationary observer see? If they could actually see this light move, what would they be seeing? I think the easiest way to see this is I'm going to act it out. So I'm going to be the truck driver driving the Einstein road down the clock, and you're going to be the stationary observers. So here's the Einstein clock. So the laser is going to go up, hit the mirror, and come back down. So this would be 1 tick, 2 ticks, 3 ticks. That's Einstein clock. So imagine I'm in a truck and I'm going this way. So I'll come over here. I'm going to walk this way while I do this. You tell me what you see. And again, look at the marker. So I see it go up, hit back down here, up, hit back down here like that. What did you see? Yeah, you did not see this. You saw that type of motion. It turns out, since there's no acceleration, it's more like triangles. And so I'll do this again. Look at the marker while I walk this way. So I'm here, let's see, they can still watch, good. So I only see this motion here because I'm at rest relative to this. So I'm only seeing it going up and then down, up and then down. It's very boring, okay? But you're seeing this motion here like this. Okay, so what you see is you see the laser go up here, hits the mirror, comes back down, another beam goes up, hits the mirror, and comes back down. Again, what did we say 1 tick of the clock is? The time it takes the light to hit the mirror and then come back down. You can already see something about this. What is that time going to be? I'm going to try to convince you that that time is going to be larger than that delta TP here. This person here is going to measure actually a longer time period, unless I should go through and work it out. And that's going to be time dilation. Again, you could say, well, wait, the only reason you're getting this weird effect is you made a really stupid clock. No one on Earth does a clock like this. It doesn't matter. Any clock you have, you can go through a calculation, a very general calculation. Any clock will give you the same result. So even though I've drawn it with a dumb clock, this silly thing, you get the same result. We're doing it this way because we can work out the mathematics easy. So let's work it out. So let delta t be the time of 1 tick of the clock as measured by the stationary observer. Okay, so now let's label some things. What is this distance here? What's moving this way? The truck. With what speed? V. How long does it take the light to go up here and then come back down? Delta t. So what is that distance? If this is v, and if the time it takes for the light to go up and down like this, what has to be this distance here? Again, could you? Well, the time it takes to go here is delta t. So this is delta t. The velocity here is v. So what's this distance here? It has to be v times delta t. That make sense? So this distance here is the velocity of the truck times delta t. Again, if you'll go back to the x equals x naught plus v naught t plus 1/2 at squared. This is 0 because there's no acceleration. You take this to be 0. The v naught is just our friend v, and then the time is this delta t. That's at x. Now, what is this length right here? What is the length on this side here? Well, L naught is this guy right here. Remember, L naught, what that is if here's the here, and if here's your laser, that's your L naught. So what is this right here? We don't know that. It might be, but I mean, we want the distance. Okay, what's moving? What does this line represent here? What's moving? The laser. What does the first postulate of relativity say? Everyone will say that that velocity has to be c. So this is the speed c. How long does it take to go from here to there? Not necessarily. If this is delta t to go from here to there, then this has to be delta t over 2, right? The time it takes to go from here and then back, that total time is delta t. Okay? So the time it takes to go from here to there is going to be half of that time. And then the speed is going to be c. So this distance here, if we do this equation again, the velocity is c, and the time is half of half of one tick. So I'm gonna put this over here because that diagram is kind of cluttered. So this is v naught t. This is L naught. Here is c to t over 2. Okay, does everyone understand how this is set up? Because the rest is now just going to be algebra. Okay, we have a friend here. Where's our friend? You recognize something. Sure? But I mean, mathematically, what do you represent? You might see a friend. If you, yeah, you're getting there. Yeah. No right-hand rule until magnetic fields. When you get magnetic fields next semester, we're going to have right-hand rules all over the place. And then we'll get some right-hand rules when we get to torque. Yeah. Oh, I thought your hand went up. Okay. Okay. We have a right triangle here. Where do we get a right triangle? We have to do something and we get a right triangle. Exactly. If I look at this right here, that's a right triangle. So if I draw that over here, This is L naught. This is C delta T over 2. What is that, fellow? Yeah, it has to be half of this guy. And then what do you do? Pythagorean theorem. This squared equals this squared plus this squared. So we have the hypotenuse squared equals this side squared plus this side squared. Now, in the words of Sesame Street, one of these things is not like the other, and it's this fellow. What do we do with this? We could. I want to get rid of it. Do we know anything about O naught? Far end here, we know this. Now we know this. We take this and we put this all the way in here. So I got C delta T over 2 equals C delta TP over 2 squared. Plus C delta T over 2 squared. Okay, something nice happens. Not quite, but something does cancel. Yeah, everything's divided by 2 squared, so let's get rid of those stupid 2 squareds. Now, if I have a delta T over here and a delta T on the other side, what would I do then? You get the delta T's together. So I'm going to cancel all the 2's, so kill all the 2's. I'm going to take this term over here so I can get my delta T's together. So if I square this out, I get C squared delta T squared. I'm taking my friend here to the other side, so that gives me V squared delta T squared. And that just leaves me my friend here, C squared delta TP squared. I'm going to divide everything through by C squared. So if I divide everything through here by C squared, this one here gives me a 1, so this gives me a delta T squared. This gives me minus V squared over C squared delta T squared equals delta TP squared. Okay, if I have a delta T squared here and a delta T squared here, what will I do? Mathematically? You pull it out. Okay, so I'm going to pull out a delta T squared. If I pull out a delta T squared here, what am I left in the parenthesis? I'm pulling out this guy here, so what would this have to be? If I pull it out here, this would have to be 1. Good. Then what am I left with here? With the minus sign. All right. This times this is this term. This times this is this term. Okay? And I divide through by this. These cancel. This tells me that delta T squared equals delta TP squared over this. I take the square root, and if you do that, you get an extremely famous equation in physics. This is extremely famous, and this is called your time dilation equation. I want to give you one other way to write it, and then I want to talk about that equation for the rest of the class. Okay, I'm going to write this in a slightly different fashion. I'm going to write this as, like this. It's the same equation. I can rewrite this as the following. The reason I rewrite it like this is this quantity here, 1 over that word square root, that occurs all the time in relativity. And you give it a special name, you call it gamma. So this quantity here occurs frequently. So something occurs frequently, you always give it a symbol. This is gamma. So gamma is by definition, okay, this quantity here. And this delta Tp here, I can now tell you why it's called the P. This is called the proper time. Okay. The proper time is measured by the person at rest relative to whatever is being measured. So in this case here, I was at rest relative to the clock. Remember what did I do? I put the clock in the back of the truck and I moved this way. So I saw the laser light go like this. I'm at rest relative to this clock. So I'm going to measure the proper time. So you measure the proper time when you're at rest relative to what you're measuring. So what I want to do is look at this, talk about it, and then actually give you some experimental evidence of why this is actually true. Okay, there's always these, okay, for some reason when, okay, this happens in every physics department. There's some group of society that goes insane, and then what they do, they decide to basically disprove physics. And it's always relativity, and it's always quantum mechanics. And then they write these manifestos of why quantum mechanics is wrong, why special relativity is wrong. And you get these manifestos. And where do they go? They always come to your local physics department. They always come to me. And so about once a year, we get these little manuscripts from people explaining why special relativity is wrong and quantum mechanics is wrong. The evidence for quantum mechanics and special relativity is overwhelming. That's already an understatement. Every single experiment shows that special relativity is correct and quantum mechanics is correct. It's just, especially special relativity. Special relativity, that is so well established, it's ridiculous. Okay? And quantum mechanics, at least the traditional form of the non-relativistic part of it, is entirely well established. There's no, this isn't kind of up to debate. This is, you can certainly question the interpretation, but not the actual theory itself. It's rock solid as far as the evidence goes for it. It doesn't get any better than that. So let's talk about and see what we can do with that. Let's ask, what does gamma look like? So I'm going to plot gamma versus the velocity. So how small can gamma be? So let's say you're not moving. If your velocity is 0, from that expression, what is gamma? Okay, v is 0. 1 minus 0 is 1. Square root of 1 is 1. 1 divided by 1 is 1. So the smallest gamma can be is 1. Now, what do you, okay, think about think of like the space shuttle when it was breaking up. And so you have 10,000 miles an hour. If I take 10,000 miles an hour and divide it by the speed of light, what do I get? Something ridiculously small. If you take a number ridiculously small and just square it, what does it do? It gets smaller. 1 minus something that's almost 0 is what? Pretty much 1. What's the square root of pretty much 1? Pretty much 1. What is 1 divided by pretty much 1? Pretty much 1. So for everyday velocity that you have, what is gamma? Gamma is going to be 1. You're not going to be able to notice any real variation on this because the speed of light is gigantic. So in everyday life, are you going to see any type of effect here? If this is 1, this just tells you that delta P and delta TP are the same, that you're not going to measure any relativistic effect. Okay. Now, what happens if I start getting the velocity close to the speed of light? So let's say here's the speed of light, c. I'm not at the speed of light, I'm not past the speed of light, I'm just near the speed of light. So if I get near the speed of light, what is the velocity near the speed of light divided by the speed of light? Not quite 1. If I square not quite 1, what do I get? Not quite 1, okay? What is 1 minus not quite 1? Yeah, not quite 0, okay? Crazy math, isn't it? What is the square root of something not quite 0? Not quite 0. It's going to be quite tiny. What is 1 divided by tiny? It's very large, okay? So what's going to happen here is that gamma stays pretty much close to 1 until you start getting around 10% the speed of light. And even then, it's very small. What's going to happen then is that this gamma value then starts taking off, and it takes off actually ridiculously rapidly. Like that. Okay? Now, let's say you're driving along, you're borrowing your parents' car, and you gun it, and you look at the speedometer, and the speedometer goes up to 2c. Okay? It's turbocharged, and it has a Hemi. Okay, so it's up to 2c, twice the speed of light. What is gamma? Let's calculate it. 1 divided by the square root of 1 minus, what is the velocity? 2c. So we take 2c. We divide this by c and square it. C's go out. You get 1 minus 4. What is that? Okay. 1 over the square root of minus 3. What is that? Yeah, this, you're going to get an imaginary number. Okay, meaning you're going to have an I in it. Okay. If you happen to be driving your parents' car, and the speedometer goes into, it says I, stop the car and run like hell. Something bad's going to happen. Just get out of that car. Nothing good is going to happen there. Okay. What this means here is you can't go faster than the speed of light. Okay. Once you go, you can get very asymptotically close to this line, but over here, that gamma becomes imaginary. You can't go past the speed of light. If you matter, you can't even go the speed of light. I'll give you another proof for that later on, once we know a little bit more. Okay. So this is what this looks like. Okay. Questions? Now, is there any? What does this mean here? How are we doing on time? Doing great. So here's our time dilation equation. This means that if I have a case here, let's say here's a let's say I'm here, and here's a spaceship, and I put a bomb here. Okay? And this bomb, the timer is set to go off in 1 hour. So this is moving this way B. So the timer goes off in 1 hour. What is that 1 hour? Is that a delta T or a delta TP? This is a delta. In other words, if you're here, you set the timer, you're at rest relative to that bomb. If you're at rest relative to the clock, so imagine like there's a little timer, you set the little timer for an hour. Like one of those little egg timers that you boil eggs with. You set that to go off in an hour. That's your proper time. Now, this is a stationary observer. What would they say about that time? Well, if this ship goes faster and faster and faster and faster, this gamma increases more and more and more. So according to this person's point of view here, depending on how fast it's going, that bomb may not go off for 2 hours, 3 hours, maybe 18 years. Okay, from this perspective here, because depending on what the gamma is for this. Okay. You can get some really absolutely phenomenal gammas if there's certain things called cosmic ray burst. And if you look at some of the cosmic rays, not many of them, just a couple of them, they have gammas which are just absolutely preposterous. I mean, you can't even get close to a particle accelerator with those values. I mean, it's just orders of magnitude, billions of orders of magnitude greater than a particle accelerator. So what I'm going to do on I'll set this up. Okay. I want to give you the classic experiment for this. This is a classic evidence for time dilation. Oh, every single particle accelerator that's built assumes relativity is true. I'm going to set it up and then we'll go over it tomorrow. So there's something in, there's a particle called a muon. Okay? You use the Greek symbol mu for it. A muon is basically, it's just like an electron, but it's heavy. This is basically it's a heavy electron. If you had a muon in your hand and watched it, it turns out it decays in 2.6 microseconds. So this decays in 2.6 microseconds. Okay, what is a micro? What is a micro? 10 to the minus 6. So if you had a muon in your hand, in 2.6 microseconds, this thing would blow apart. Now these are actually produced in the upper atmosphere. So here's the ground. If here's the atmosphere. Okay. It turns out that these muons are produced up here. They're produced when cosmic rays basically have the atoms in the atmosphere. They're produced. And you get this cosmic ray shower coming down, but you get these muons. And these muons can be going at, let's say, a velocity of 0.999% the speed of light. I'll just put this in here. So they're going at 99.9% the speed of light, which is very routine for these things. Okay, that's a very common thing. Okay. How thick is an atmosphere? An atmosphere here is something on the order of like 10 kilometers. Okay. If relativity isn't true, what should happen? Let's say all this relativity crap I told you about is garbage. None of it's true. Yeah, you're traveling this speed, okay, for this long. These particles, and we'll work it out tomorrow, are going to basically decay here. Well, you go and you try to measure these things. Where do you find these particles? All over the surface of the Earth. Okay, so what we're going to do next time, we're going to actually go through and work that out. We're going to come back and revisit this. Have a great day. Again, if any of you are quarantined, let me know, and then I'll send you the exam on Thursday.